Thanks very much. Everyone can hear me all right? Yeah, thank you. So yeah, thanks very much, organizers. Thanks, Jens. Thank you all for being here to my very weird talk. When I was invited, this is what I did during my pandemic, and so immediately assumed this is what we wanted to hear. I've mashed this together with hopefully some distinguishability and platonics discussion later on. We'll see how that goes. Haven't tried this before. Yeah, going to talk a little bit about this this new organization in Sydney and hopefully make it interesting. And maybe the way to do that is to talk to it in terms of, how might you go about getting on the orders of tens of millions of dollars from your local governments to do quantum stuff. So let's think about it that way. Right? You're all on board. So first you get some trusted source of information to write a kind of quantum landscape. This is 2 years ago. CSIRO, the Commonwealth Science and Industry Research Organization in Australia, to talk about quantum, to rattle off some of the different quantum capabilities around the country. And then the chief scientist of Australia makes that even more specific. And this is quite dangerous when they start looking at, kind of areas of quantum expertise around the country. And we heard from our colleagues in Queensland on the ion trapping side earlier this week, for example. So you want to be careful here when the chief scientist starts doing this, but it is good news. And you make sure that they put something like this in that report, because I don't know how many times I've seen these two numbers in the last year and a half since I moved to Australia. 4 billion revenue by 2040 and 16,000 jobs. And so then you get members of your community to start writing for things they don't normally write for, like the Australian Strategic Policy Institute, around how important quantum tech is. And then the ball's really rolling. I'm being facetious, this isn't really the order that things went in, but the government explicitly lists quantum tech on their list of critical technologies. You have announcements just last November on the order of $100 million for quantum stuff. But then you get a new government, and they're making smaller promises, but still the orders of millions of dollars. This one specifically around training, and this one actually specifically mentions the SQA in this election promise that we're now helping them fulfill. So there you go. That's how it works. Then what you do is you have to. This is really, like I say, in the other order. You have 4 universities demonstrating a very impressive concentration of quantum tech skills across very many different areas. And this is always dynamic. And we made up some of these very short descriptions of people's research. And trust me, they're not happy about the way we did this. So you don't have to tell them, they know. And there you have it. Now you have kind of this, hey, why don't we, oh, sorry, one more. You can go and put research stats together, or have the university offices do that for you, that you can then put in front of the government as well. With the SQA kind of well represented if you select the data right, and off you go. Okay, so what the heck is the Sydney Quantum Academy, finally, that you lay the groundwork for it? So I think it's a pretty unique partnership. I should say I was at University of Bristol in the UK before this. This is what led me here, in director of one of the centers for doctoral training. And this is kind of like that, but it's across several universities, and it's got state government involved. So it was established just a couple of years ago, and in fact, it was established before I got there. It is an unincorporated joint venture between the state of New South Wales, where Sydney is, and these 4 university partners. So roughly half the budget comes from the state and half the budget comes from the 4 partners. So you use this kind of leveraging model. And then you get people together and you brainstorm some vision statement. And this is very, very carefully selected: building Australia's quantum economy. The SQA is not a research organization itself. We're a small team. I'm the only academic on it. But the mission then is to kind of harness all of this amazing expertise and go out, this academic industry government triangle, if you like, that so many kind of quantum ecosystem builders around the world are doing. And so when it's appropriate, you might speak for that academic community. But again, you have to be careful there. And then some specific objectives very much around talent, as I said, both training talent and attracting talent and investment. Really that engagement side with industry and government. You're kind of like a portal, if you like, for universities and state government to use when they need quantum expertise. and promoting, getting the message right, being careful, promoting responsible use and development of quantum, but also trying to maintain enthusiasm while not overpromising or trying to rein back some of the things that are going on. It's a fine line. Anyway, you also need to make sure that you have to convince your funders that you're well governed. So just this is one way that you might set things up. Like I say, we're a small team. In the middle, we've got an executive board with some independent members and some representatives from the 4 universities. We've got a technical advisory committee that really talks about the training and whatnot across the 4 universities. The students are feeding into that, and then you've got an external advisory board with some names that we all probably recognize, or several names that we all recognize, and getting that industry input. Okay. So one of the first programs that were up and running, so the kind of key is PhD scholarships. So one way, and I mean, one of the major components of the SQA is basically a graduate scholarship program. Currently up to 125 scholarships. Those aren't all full scholarships. They're also partial scholarships and whatnot. Recruiting internationally. So, and one of the unique features here is that these students can take courses being offered at all 4 partner universities in a kind of goodwill type arrangement. And it has these transferable skills and these extra things that are quantum and more widely physics graduate programs are adding at various training centers around the world. You also do undergraduate programs, so we're getting students from all over, or we're trying to expand it to get students from all over to come to Sydney and spend some time in there. Also trying to get this cross-institutional thing going on across the 4 partner universities at the undergraduate level, so that, again, a student from X can take a course at Y in the quantum area. And things like putting an internship database together, which is already taking expressions of interest from students and then listing whatever industries might have positions and trying to help matchmake. And this is open for international industries as well. If you wanted to have your favorite industry with an internship, advertise it if you like on that database, you're welcome to. So then you have a website portal, like I say, and we've got this list of over 100 quantum experts. That's staff and kind of research associate level people in Sydney that students or whoever can go to and look up and say, do I have a project, and learn how to apply to the SQA scholarship program, for example, through this kind of thing. Find a potential supervisor, talk about a project, and then go straight into the application process. And then I talked about how the chief scientist was talking about capabilities in different areas. And you might want to do that a bit more carefully. So we have our community self-identify of where they sit in this Venn diagram of computing, comms, and sensing. You'll notice it's not it's not a complete list of names because we rely on sending emails to people, and often academics don't like to respond to such emails as I'm learning. But anyway, you can feed this back, of course, to the funders and whatnot. And so on the engagement side, the types of things that we do, we're running a future skills assessment. This kind of thing has happened in the US already, trying to gauge with Australian industry, what are the talent needs that the industry is going to need going forward, having that conversation, getting people thinking about it, and feeding that back to government. Again, engagement proper, events, public industry facing events, workshops. We've done things with, InsurTech Australia and other examples, and just a recent one this week on quantum related infrastructure in New South Wales. And you run a Quantum Innovators Network for entrepreneurship, the startup community, getting the startup community and the academic community together, meeting every couple of months, and make sure that those students that are in your program are coming to this thing as well in order to get that exposure. Okay, so this all happens, this is all made much, much easier when you have a place, and we finally do, and pandemic certainly set us back on this one, but we are in, believe it or not, we did not call it the Quantum Terminal. Transport New South Wales did. It is literally the old Sydney Central train station where Transport New South Wales was, and then moved out to their new facility. So in that nice old building, if you've ever been there, right near the center of Sydney. So we're there as an anchor tenant, startup type of space. There are several quantum startups, and again, we kind of help try to recruit into this space. Several startups already taking a few desks there. And it's a focal point for the quantum community. This is up on the 3rd floor, which is a great event space where we have these student seminars, these workshops, these whatnot, the Quantum Innovators Network, these kinds of things. So trying to make a focus for all of this activity. We run a annual national conference, a very industry-facing one. I think it's fair to say the first one last year was quite successful, and thanks to those of you who were involved. We'll be running it again in February coming up, and I encourage you to have a look and come and visit now that we're open for travel, if possible. It was really quite good. A very strong mix between the industry government side and the academic side. And so, yeah, I'll just say, I mean, this list is in no way complete. I did this off the top of my head a little while ago, and I've given up trying to update it. But like, we're joining this growing list of very quantum-specific training programs and entrepreneurial programs. I didn't talk about a proposal we have in the government to do this kind of thing in Sydney. And industry bodies, dedicated quantum industry bodies. And I guess I just wanted to finish this section to say that the Australian industry community has come together just literally yesterday. There it is, under the umbrella of something called Tech Council Australia. So Australia has joined the ranks around the world of these kind of quantum-specific industry bodies, and they're calling it Australian Quantum Alliance, which sounds a lot like Mid-Atlantic Quantum Alliance down south of here. Yeah, it's hard to keep track of these things. And there's a few of the startups and the global industries that are involved in that thing. So just an update on that. So I hope that wasn't too boring. I think that's all I wanted to say about the SQA, but I'm more than happy to talk to you about how we do these things. And I've had at least one curious attendee, how what we're doing might inform some of the things that you want to do, because as we know, this is happening all over the world. Okay. Do you want to, questions now might be good. So the initial tranche of funding was 5 years. And we're about halfway through, a little more than halfway through that now. Yeah. So those conversations are ongoing on what the next stage looks like. Yeah.
What would you think of as possibly the minimum size of a community that would be necessary to get something like this off the ground? Say, for
Brisbane. Maybe you tell me. It all depends on the scale. Something of this scale, I think you do need. So the chief scientist of New South Wales was very clear. They wanted the multi-university thing going on. They wanted, they're looking for things that several universities can do together that one university can't do on their own. So I think that's one of the criteria in something like this. But it could scale. And certainly there are the CDTs in the UK, for example, are just a training program at a university, that kind of thing that could be argued for. Yep.
Is there money for buying, dedicated for buying equipment and stuff like that?
Well, yeah.
Sorry, go ahead.
Well, yeah, again, not as a research organization, we don't run labs or anything like that. The students have career development funds that, for appropriate uses can be used for stuff like that. But I mean, not.
So you're not like a fund.
Just it's better like a scholarship program on that side of things, and then all the engagement program as well. So we're a very academic organization. You saw the governance board. It's mostly academics at the 4 universities, but operating in this area between industry, government, and academia. And I should say that government, maybe going back to the previous question, government, and I think all organizations like it when they can send all their questions to one place, and so for understandable reasons, and it's not always something that you want to play that role, but another feature, if you like. So anyway, yeah, please, now that things are back on, please come and see us. If there's students that might be interested, please let them know. And the door's always open for questions and whatnot around this. Is that okay for that part? Okay. All right. On to distinguishability and photonics. So complete gear switch here, everyone. You take a breath. So I'll confess it's a little embarrassing to come up and spend your people's time talking about more administrative things. This is stuff that's some of this formalism certainly is a few years old now. I've spoken about it before, and I just thought I'd add on a few thoughts that I've had over the last little while on this kind of formalism that we have, especially leading into our next speaker's talk. So without further ado, we were very lucky yesterday to have several discussions, earlier this week as well, several discussions focusing in on quantum interference, in particular the Hongel-Mandel experiment. So I don't need to really go over that, except in one sentence to say that this is where you put two photons onto a 50-50 beam splitter, and as you change their distinguishability, if you like, in this case, in the original experiment, timing, you get to, as they go through this, as you make the timing the same, you see this dip in coincidence counts. This was discussed in Nicolas' talk yesterday, for example. So that's the thing to have in mind as we go forward here. And the question here is so this time and degree of freedom, if you like, is playing a role of the distinguishing degree of freedom in this experiment. And these spatial modes are the active, if you like, the system, as we would call it, that you're the thing that you control in the experiment. So how do we model distinguishability? I've done this talk a few times, but it really just boils down to this. I take my creation operators in those system modes, S, and I add a label mode, L, so that these creation operators become doubly indexed, okay? That's it. And can argue about what exactly those label modes look like. It can be all sorts of different things, but in terms of the formalism we want to look at and getting the features, a big chunk of the features of this distinguishable situation, that's all it really is. So I like to write, because this thing now has two indices, I can't help myself but write them as arrays. So here's a good old-fashioned indistinguishable state that you might find in a Hom experiment, where now I'm using polarization notation as the label degree of freedom, that second index, L. So here's two horizontally polarized photons, one in the first mode and one in the second mode of some interferometer, okay? No problem. So there's nothing special about that. It's just a Fock state written as an array instead of a list. That's it. Okay. So of course, a distinguishable state would say, okay, well, let's let the photon in the lower spatial mode be vertically polarized, for example. Is that okay? Pretty cool. All right. So maybe as a, again, it's pretty basic, I guess, but it gets interesting quickly. So maybe some people might know the answer to this, but think about that state for a little while. Is that indistinguishable, or what would you call that? And we'll get back to that as we go on. Okay, so there were questions on Tuesday about first and second quantization, and Rob mentioned this at length yesterday. So I think in terms of this, so I want to go to first quantization. That's why I'm talking about this. Obviously, we've just been talking about second quantization, where the systems, the Hilbert spaces, are modes, simple harmonic oscillators, and the states, if you like, the basis that we choose for that Hilbert space are kind of particles in the form of occupation numbers. Okay, and when you play around with these operators, you get symmetrized unitary. If you're doing unitary evolution on these things, you get symmetrization through the commutation of the operators. In first quantization, it just, in my mind, very, very bluntly or simply, it just switches. The systems are now particles, and the states, the basis for those Hilbert spaces that are now finite, are the modes. Which mode is that particle in? Is that okay? So that's all I mean by first and second quantization here, and I was speaking to Rob yesterday about his coarse graining map and whatnot, and I think we figured out that he was talking about something slightly different. So this is really just one-to-one stuff. And you've got to go in and symmetrize, undergraduate textbook, you've got to go in and symmetrize those states by hand now, because the formalism isn't doing it for you. But the unitary action is now kind of transversal. If you write this as a circuit where these are now qubits, it's this big untangling symmetrization, and then the unitaries are just the same unitaries happening to each of the photons in this interferometer, for example, okay? So what's a key observation here, this is going in a very quantum information way by first quantizing quantum optics or photonics here. We have, I want to think about, systems and labels, I want to think about the label here is an environment. It's like an environment that each particle carries with itself, right? That's serving to distinguish it. So that is not the tensor product structure of the second quantization. I've got ds times ds is the number of system modes and dl is the number of label modes. And in this model, I've just got ds times dl harmonic oscillators that I'm creating excitations in. That is not a bipartite tensor product structure. So in the first quantization, we get this. So I'm talking about qdits that have a ds dimensional degree of freedom and a dl dimensional degree of freedom in general. Again, and the idea here is I've got a photon and interferometer. There are ds ports in the interferometer, and it could be one of dl colors or polarizations or whatever. Okay, I've got n of those things. So just again, textbook quantum information. I tensor for each of these particles. I tensor it together, and then I've got to go in by hand and symmetrize this big Hilbert space. Yeah, okay. First quantization, and here's maybe just the whole talk really just boils down to this observation that Hilbert space has a decomposition. It looks a lot like Chervil, if you've seen Chervil decompositions of qdits. But I'm just decomposing the symmetric subspace of these bipartite particles. And what that notation means, if you don't do this kind of stuff, this is the Hilbert space for a representation of the unitary group ds, unitary operators on the s degrees of freedom, the s system states, if you like, and tensor together with possibly a unitary action on the other degree of freedom, the label degrees of freedom. And then I sum this up in sectors across different IREPs, lambda, which I'll be using Young diagrams to take care of going forward. But I hope, so I mean, let's make a simple example. But yeah, that's the key observation here. So indistinguishable state, we already said a few slides ago what that looks like in the Fock picture. In the first quantized here, I'm going to say, oh, particle. I introduced two completely fictitious subscripts 1 and 2, particles 1 and 2. There's no physical meaning to that. This is just how I write them on pieces of paper. I say photon 1 is in the first mode in its H, and photon 2 is in the second mode in its H. I symmetrize those things with a permutation action on those fictitious labels. That's where the permutation group acts. I then, on the third line, I rearrange the tensor product, which I'm free to do. I'm just changing the way I wrote down the order in which I write my Hilbert spaces. And I see, hey, there's a symmetric combination of the system degree of freedom and a symmetric combination of the label degree of freedom. And I just write that in group theory, in representation theory language with Young diagrams. But it's just an introduction of notation there, okay? So, the quantum information theorists around, we say, oh, okay, there's a separable state of two particles across the system label tensor product. Okay, slightly more complicated, so I didn't write it down, but it doesn't take long. That if I try to do this with the distinguishable state that we talked about a few slides ago, I get a superposition across two different symmetry sectors, if you like, of this decomposition of the symmetric subspace. I get the symmetric part, but I also get a contribution from, in this case, there's only two particles, the antisymmetric part. Is that okay? And again, you would just derive this exactly the same way, and there's no tricks or anything going on. Okay. All right. So now we can look at Hom in the first quantized picture. So again, just rewriting, I've got this indistinguishable state written in first quantization with this kind of symmetry adapted basis. I've got this distinguishable state, as we just discussed, is this entangled superposition across these two sectors. And I can just go off and do quantum information theory. I can trace out that label right now if I want to, and just talk about unitary operations, unitary evolution on the system degree of freedom, which is what the interferometer is doing. And as we know, I think most of us know now that in the symmetric sector, that unitary evolution is given by permanence of these manipulations of these unitary matrices. And maybe lots of you do know, but in the antisymmetric subspace, it's not hard to believe that what you get is in the antisymmetric sector, which you normally wouldn't see, right, with indistinguishable bosons, is this evolution is given by the determinant of that unitary matrix. So the scattering amplitude from coincidence to coincidence that we're looking at in HOM, it goes like the permanent of that matrix for the symmetric sector, but it goes like the determinant of your unitary matrix in the antisymmetric sector. No matter what interferometer I put this antisymmetric state through, I should say, of course, sorry, the total state, of course, is symmetric, right? I mean antisymmetric in this system. The determinant of a unitary is just a phase. It doesn't see the interferometer. And by the way, this is a much more formal way of answering a question that Ephraim asked me during my PhD qualifying exam many years ago. How do you get HOM? You do either a mixture or a superposition of these two things, and you dial between the two. And as your antisymmetric component disappears, you get a dip because you've picked a 50-50 beam splitter that has no permanent. And there you go. So we've modeled HOM in first quantization. Is that okay? Right. This is completely general and exact. Any number of particles, any number of system modes, any number of label modes. This decomposition is true. I can choose to write the states in this form. This is just the states inside that decomposition, where I can't write general Young diagrams. I've just got this symmetry. I've got this index counting multiplicities. I've got a occupation number, it turns out, and what we call an inner multiplicity. So this is just the quantum numbers associated to this thing. I don't know if Aram's here, but it's very similar to the notation in his thesis for this kind of stuff. So for example, if I've got two photons in 2x2 modes, which was the HOM situation we were just looking at in the model, very quickly you probably can figure out there are 10 Fock states available. And that's exactly because we're in two modes. We're talking about SU2, which is good old-fashioned angular momentum. I've got two spins, if you like, two qubits. If they're symmetric, I get triplets. And here I'm taking the general states are I've got a couple triplet to triplet, and there's 9 ways to do that. And of course, there's also that antisymmetric one on the list as well. There's one singlet with itself, or with the label singlet, and there's one state there for a total of 10 states. So I mean, that's just an example of how this isomorphism works between these two Hilbert spaces. So of course, we saw the indistinguishable state. I took this symmetric state on the system, and I just coupled it to a symmetric state on the label, and this is the one that we just derived. And now going back to the little puzzle I put on at the beginning, what if I just take some other symmetric state of the label degree of freedom? That's perfectly valid. It's in the Fock space by this isomorphism. What is it? Well, it's that state, indistinguishable question mark, that we started off with. So the point here is that, I mean, again, I'm sure people have talked about this state on the second line or the bottom line. I have a feeling there's been lots of discussions about it. I bring this up with people, I get different looks. Can you take the superposition of two entirely classically distinguishable situations and get something interesting? And what this is saying is that you get everything. As far as the interferometer is concerned, these are the same state. Yeah? So that's kind of a motivation for saying, hey, this distinguishability stuff, there's still interesting stuff going on. And that's where we're going. So just very briefly, we've used this in the past. We now have a kind of quantum information approach to bosonics. You can look at this tracing out business and be like, oh, the HOM test is just a mixed state discrimination protocol. I just want to discriminate these perfectly indistinguishable states from these distinguishable states. And if you have a PhD student like Stasia Stanisic, who's a ninja, you can go off and optimize and find circuits that optimally discriminate these different kinds of distinguishable states from the perfect state. You recognize immediately what a circuit for boson sampling, like a circuit for noisy boson sampling looks like, a quantum circuit, and it's clear now what its relationship to the Schur transform is. So you can play around with that. And you can even kind of use these first quantization ideas in doing classical simulations of noisy boson sampling as well. So these are things we've done in the past. How am I doing for time? Is it 5?
4 minutes for the talk and then more questions.
Okay. So, so here's just some speculation, especially leading into Scott's talk next, I think. Yeah, so we kind of argued already in this very, very simple 2-photon example that maybe superpositions of these, maybe engineered distinguishability might be interesting. And this comes from when I first saw the boson sampling paper. I think, unlike most people that are thought about, quantum computational supremacy and all this kind of cool stuff, I said, wow, I've never seen that construction of the totally symmetric representation of the unitary group before. This manipulating these unitary matrices according to the occupations and then taking permanence. And immediately, can I do this for other representations of the unitary group? That was the first question I had that I've been struggling with for a while. It's related to these things called immanents that you probably might have heard of as well. The symmetric immanent, there's an immanent for all these different representations. The symmetric one is the permanent, the anti-symmetric one is the determinant. We've seen this play out in just the Hom example already. But there's all these different, as you grow the number of particles, there's all these different representations in between. And it's this permanent determinant thing, but this is called the character of the symmetric group. It's a one-dimensional group function, a complex number that you relate to the different permutations. So I guess another way to think about boson sampling is to say I'm sampling from the totally symmetric representation of the unitary group. Now I'm saying, oh, let's insert some distinguishability. Can I sample from these other representations of the unitary group? Is there any facility in that? Maybe. I'm just pointing out that that's what you get. And in discussions with Alex Jones in Bristol, we talked about, hey, Pete, can you write down those states for me that I might want to make? And it's not too hard to do. You can just do these symmetrizations and then invert them to solve for interesting states. And there's an example of 3 polarizations in 2 modes that is going to transform like the mixed symmetry irrep. But you can also just start looking at these Fock arrays and noticing the symmetries right away and doing the kinds of things that group theorists do, look at them as couplings from smaller groups or whatever. You can just write down, well, maybe not immediately, but after staring at it for a little while and thinking about it, you can write down the 3-mode singlet, if you like, for 3 distinguishable particles. And remember, these are Fock arrays. These are occupation numbers in different modes. But they are also the defining representation of S3 on 3 objects. And so I just write these Fock arrays down and weight them with exactly the sign function that I would if I was doing this with actual states that S3 was acting on. And it turns out that this is the anti-symmetric combination. So there's lots of ways to use this form of MBS. So you could imagine creating these states and then accessing these different irreps in the lab and sampling from these distributions as well. I guess maybe with my final observation here, if you were doing this, again, going back to this very simple, so I'm just sticking 3 photons now into that Hom situation, two spatial modes, 2 polarizations. And I might ask myself, okay, I'm going to put some distinguishability in there. What representations of the unitary group do I need to worry about? And you do it however you like. Young diagram, tensoring together Young diagrams. Oh, I'm going to have the totally symmetric one and these permanents, and I'm going to have this mixed symmetry one. I've already implicitly been talking about this. It says, okay, this is going to be a 3rd-order polynomials. This is going to be 3rd-order polynomials. I've got to go and do all these calculations, but if you do this in angular, this is a very simple situation. If you do this in angular momentum notation that physicists recognize, I know I tensor 3 spins together. I know I get spins 3/2, and I get 2 copies. The 2 is just a technicality in this conversation. And I get 2 copies of the original representation I started with. So there's no calculation I need to do to figure out the scattering amplitudes in this very simple example. I don't have to compute any permanence or any immanence or anything. I just recognize that that state on the previous slide, the top one, is going to scatter like the original matrix that I had in my defining the interferometer. And you can see this play out. I asked mathematicians about this. This must be known. It's saying, oh, this third order polynomial that is defined, the scattering amplitude is defined by, goes like this imminent, and that imminent collapses. That imminent is really just something times the determinant. Okay? So very speculative. Could I use this as a verification type of thing? Could I imagine cooking up states like this and saying, hey, I use the whole interferometer, I use the same number of photons, I introduce some distinguishability, and there's a much easier way to see what this state is going to do, and then I could build up confidence about what the fully symmetric version might be doing. So there's a bit of speculation at the end. I think that's it. Thanks very much.